All right, this should be the last video in this lecture. So I want to quickly go over some basic properties of the cross product. So if I have three vectors, A, B, and C, and then this C is a scalar. First off, we've already seen that A cross B is negative B. I'm getting tired today. A cross B is negative B cross A. What does scalar multiplication do? If you have a scalar in the first component, you can factor it out. And actually, it's the same as if it was in the last component. You can factor it out of the whole thing as well. Cross products break up across sums the way that you think they should. This becomes A cross B plus A cross C. And the last one is really interesting, and I want to focus on this in just a minute. But this is actually called the scalar triple product. Why is it called the scalar triple product? Well, look at what you get. When you do this, your final move is a dot product. Dot products give you scalars, and it's triple because there's A, B, and C. And so it turns out that it's saying that A dot B cross C, you can sort of interchange these somehow and regroup A cross B dot C. These are the same. And so let's look at the geometric significance of this. I'm going to copy our formula, and then we'll come back and see sort of the equality side in a minute. But let's put that here. I'm going to focus on this side for now, and I'd like to sketch the situation with three vectors first, then we'll try and see and understand. So the picture that I want to sketch with you is we're going to do this side. So this is going to be my vectors. Let's say this is the vector B, and let's say that this is the vector. Actually, you know what? Let's make this one C. That way everything lines up the way I want it. That one is C. This one is going to be B, and then I'm going to draw A coming up looking something like that. There's my A. Is everybody happy with that? Hopefully. All right, so just like anytime you have two vectors, there's two non-parallel vectors, there's an associated parallelogram. I didn't quite draw that right, but you can imagine it. Anytime you have three vectors, none of which lie in the same plane, there's an associated 3D object, and it's got an awesome name. It's called a Parallelopiped. So I'm trying to sort of sketch it in. I hope you can imagine that, because that was a horrible sketch. Something like that, maybe like that. There we go. You're just copying each piece. I should use my slide and drag feature to actually do it, but I don't care so much about drawing it perfectly. There we go. You can always extend these three out to a parallelopiped. Parallelopiped. Hopefully I spelled that right. All right, and so I'm interested in thinking about how on earth this thing, what this has to do with the associated parallelepiped. So let's start with this formula, and let's realize that A dot B cross C, by the property that we discovered in the last section, this is the same thing as length of A times length of B cross C times the cosine of theta. Do you agree? That's anytime you have the dot product of two vectors, it's the length of one times the length of the other times the cosine of theta, where theta is the angle between them. Now I'm going to rearrange things ever so slightly just to help us see. Sometimes it's nice to have an ordered difference so that you can see what's going on. I claim that I've done absolutely nothing. I just rearranged. All right, now, pause. With this formula in mind, let's look back at our parallelepiped. I think I'm going to obsess, and I'm going to do what I said I wouldn't do. I'm so sorry. And I'm going to drag it there, and I'll put the arrow on the end. And then I'm going to, I need to do another copy. It's going to be up. There's going to be two more copies. I don't know. This might be more than I can do. It's going to be somewhere like that, and then I'll do another one. Oh my goodness, what am I doing? Something like, I don't know if you can see that one, maybe. Do I really want to do this? No. Copy, and then we can start pasting. So one there. Oh man, this is so bad. And then one here, and then one here. I should have done all of these first, I guess. Oh well. And so that one is going to go, oh no, nothing is working. Well, whatever. I'm going to erase all of these. There's a parallelopipe, and I tried to draw it, and I completely crashed and burned. But you can imagine it because you have a good mind. And I want to think about its volume. So the volume of a parallelopipe is actually equal to the area of the base times the height. So let's focus on the height of this guy, right? The height here is going to be something like this. There's this height h, and we want to figure out what that height is. And so if you think about what's happening here, first off, I need to somehow tie a vector into a vector that's pointing straight up out of the BC plane. Oh wait, that's the cross product. That's the cross product B cross C. So I'm going to think about this vector here. I don't know how high B cross C goes, but I know that it's what I want. And then somewhere along B cross C, let's just do it in red, somewhere along B cross C, I've actually got the height of this parallelopipe. Does that make sense? The parallelopipe is actually over here somewhere, right? It's all over here, but you can realize that it does have a certain height that's sort of sliding across there. And I'm interested now in the angle theta between A and B cross C. What is that angle? And when I think about it for just a moment, I realize that if I compute the, let's see, I'm going to imagine that this is a right angle right here. I'm forming a 90-degree angle. So if I do, think with me, if I do the cosine of theta, I get the adjacent over the hypotenuse. So let's notice that cosine of theta is the height over the length of A, and so that means that my height here is exactly length A cosine theta. Oh my goodness, are you seeing what I'm seeing? This is exactly the height. And what is the length of B cross C? That's exactly the area of the parallelogram. This is the area. And so it turns out that the scalar triple product actually gives you the volume of the associated parallelopipe. And I just want to apologize to you for the 30 seconds or so of your life that I stole from you by trying to slide all those vectors around. I'm sorry. That is it for this section. Great job. I'll see you in class soon, hopefully. Ciao.